Hello, everybody. We are going to continue and finish today the closest pair, start linear programming probably. So we'll be synchronized with my two courses, slightly shuffling it. We were supposed to do it slightly later in the course, but for reasons it fits very well to what we are discussing now. So we'll move to linear programming to synchronize. Some of you know what I'm going to speak about, so you don't need to go for it. The difference between the linear programming that I'm teaching in this course and the linear programming that I'm teaching in computational geometry is that in this course we'll talk much more about integer linear programming applications and higher dimensions and a bit less geometry.
This will be a part of linear programming, right? The
Sorry?
locating points problem will be the part of linear programming. The locating points problem will be a part of linear programming.
That has nothing to do with linear programming. That is a topic by itself of finding the closest pair. It's not a linear programming problem. Okay. But it shares some ideas with what's going to happen in linear programming. So yeah, we're getting used to some set of ideas that we are going to recycle a few times. Any other questions before that? Since I gave extension to homework 1, any questions that you still have for homework 1? People asked me yesterday, I felt very guilty. Okay, everybody's good with homework 1. Fine, you have homework 2 today, but I will wait with discussing solutions for Wednesday. So our problem was we are given a set of points. I'm just reminding you the notation. So a few notations that we used. Our problem in general is we are giving a set of points, S. We want to know what is D of S, which is a distance between the closest pair of points in S. We'll assume that there is no point that appears twice. Here are a few points in S. And presumably here is the closest pair because the distance between these two guys is larger than the distance between any other pair. Okay, and I don't see the chat just to see that. Okay, yeah. So, and as usual, I'm Zoom people. I'm also on Twitch, which is much less compressed. It's alone LG. LG on Twitch. Okay, and said we can check every pair of points to see what the distance between them. Trivially, now that will be n squared. We know that deterministic algorithm will run in at least n log n, omega of n log n, because that was a reduction from the element uniqueness. We cannot really find if two keys appear twice in algorithm in deterministic way. Deterministic meaning we don't toss any coins, we don't let anything for randomness. but we are aiming toward a linear time algorithm, which would be much better than the n square naive algorithm. But at the moment, we are definitely not getting there. So I'll remind you what's the basic data structure that we used. We are constructing a grid at its incremental algorithm. We are looking at S of I, all the points start at P1 all the way up to Pi only, the subset of the big set altogether. And at each iteration, I'm incrementing I. That is, I'll start with S2, which would be P1 and P2. I'll compute the distance between them. Then I'll add P3, then P3, then I'll add P4, and so on. And each time I need to update the distance of the closest pair, if needed. We created a grid, and the grid has infinitely many cells, but we don't let it disturb us. This grid has infinitely many cells. The size of every square, every cell of the grid would be d of Si half. d of Si half. d of Si over 2, horizontally and vertically. And I argued in the last meeting that from Si, I will never have 2 points in the same cell. I might have other points which are in Pi plus 1, Pi plus 17, points in the future. But from the point of Si, I will not have 2 points in the same cell. Why? Because what's the length of the diagonal of this cell? If this is 1 and this is 1, then the length of the diagonal is square root 2, which is less than 2. And I assumed at the moment that the distance of the closest pair is 1. I normalized it otherwise. Okay. And then I used a hash function, hash table. I store for only the non-empty cells, the cells that have a point of Si. These are the only ones that are stored. The key that I store, that I use is if the size of the grid is 1, then it's the floor of X of each point of the cell and the floor of Y. So it's like first name and family name, if you wish. We'll talk more about hashing, and you'll see that if we have a key that consists of several fields, it's really not an issue. If you want to know how to do the overall hashing completely, if you have 2 keys, K1 and K2, one possible way to do the hashing would be take some constant, called it A, times K1 plus another constant times K2. Maybe you need to, if these constants are non-integers, then you need to make them integer and do modulo M, where M is a table size. If and these 2 guys are constants. That's one possible way to perform hashing, hash function of the cell. And with every cell, I store the unique point inside the cell. Now, give me any point in the cell, any X and Y. It might be a float numbers, but to get the index of the cell, the key of the cell, the moment that I'm doing the flow, then 2 points, 2 fingers in the same cell. What happens to them? The difference of the X would be less than 1, so the flow will give me the same value. The flow of the Y will give me the same value. To be precise, I'll get the coordinates of the lower left corner of the cell. That would be the index of the cell. And that's what identifies each and every point in the cell. Out of the infinitely many points, not only data points, all the points in the cell, they all have the same key. Now, what happens if I'm adding a point, and because of the new point that I just added, Pi plus 1, the grid size needs to be smaller. So now delta is just a shorthand of d of si half. Now the grid size instead of 1 is every such cell has size delta, and using the very same trick, the key of a pair x and y of a point xy is x over delta and y over delta, floor of each. Just rescaling. You know, the scale is big, smaller.
Shrinking the grid size?
Yeah.
Shrinking the grid size?
Yeah. But, because I'm doing it, then now my hash function, k1 and k2 were integers, but now they are different integers. The same point now needs to be stored at a different hash table, different cell of the hash table. So I need to, if delta was changed, then the keys of all the points are changed, and we need to rehash, that is, to recompute the hash function of each and every point of si plus 1, because I added a point, but with another point that is added, and we insert all these points. Just a process that, as you probably have seen in 345, it's called rehashing. Take everything from the hash table and reinsert it with a new hash function. By the way, if you are using the dynamic tables technique, then you can use this opportunity to double the hash table if needed. But it's not really needed, because how many items do I need to store? It's at most n, right? So I know how many keys I'm going to have. So the hash table would be about 2n. We like to keep the hash table about twice the size of the input. Remember, why at most n, many hash cells? Because every I keep 1 point. One cell contains at most 1 point, and I only keep the non-empty cells. And notice that by using the hash table, if now we will have a query point that landed right here, it might be a data point or not a data point, I don't know. But if I have a query point, Q, I can find if there is any point of Si that is in the hash table, any point of Q in the cell of the grid that contains Q. Convoluted sentence. I have a query point where my finger is. I want to know if there is any point of Si. I'll just compute the key of the location of my finger and perform find in the hash table. The moment that I'm doing the floor is taking my finger and bringing it to the lower left corner of the cell. And now I have the index of the cell, and I'm performing find in constant time in the hash table, and it says this table, this blue one, is empty. If my query point is right here, then I'll get that this anonymous point is in the same cell. Questions so far? Zoom people, by the way, Zoom people, do you have any homework questions? You're muted. Okay, cool. So we have this function, or this data structure, and now I'm trying to get to the next slide. And if I need to rehash, just to highlight what is rehashing, take all the points out. Now we have a new grid. Gamma hangman, this letter over there, big gamma, is a name of the grid. Age is a hash table. And rehashing with a new D of Si. D of Si has been smaller because I added a new point. No, of course, I'm only adding points, so D can only shrink. When I'm adding a point, either d over si didn't change at all, or become a bit smaller. So rehashing, just construct a new hash table. The key now is d of si is the new one, and insert all the points. Well, how much time does it take? It's important. It's order n, obviously, but we'll actually be quite happy that the running time is linear in the size of si. It's order I here, right? Si has I many points. And we are going to take advantage of that it's linear in I. That's the number of points that I'm inserting. Okay. So far I have the points P1, P2, P3. I'm about to add P4. Pi plus 1 going to be P4. And I have P1 S3. S3 is P1, P2, P3. D of S3 is, let's look, the distance from here to here, the distance from P2 to P3, the distance from P1 to P3, which is the smallest P1 to P2. I'll take this distance, divide by half, that determines the grid size so far. Okay, and P4 is just appearing. And maybe because P4 appears, I have a new closest pair. But once P4 is joining P1, P2, P3, maybe a new closest pair is found. And of course, if it's found, then one of its members of this closest pair is the newcomer P4, obviously. Where is the other point of this closest pair, if any? Where should I check? Obviously, if there is a point in the same cell of P4, definitely it's very suspicious. It might be the new closest pair. I'm still not sure that it's a new closest pair, but definitely D over Si is going to decrease. Okay, so I need to check if there is any, I'm using the hash table to check if there any point in the cell of P4. There is none. Does it mean that P4 doesn't participate in the new closest pair? Could be that because it's going to create a new closest pair with P3, which is not in the cell of P4, but it's in one of the 8 neighboring cells. So I'll check all the points in the 8 neighboring cells. What do I mean? I'll compute for each one of these 8 cells what is the lower left coordinates, just perform a query in the hash table asking if there are any points of Si in any of these cells. Could be 1, could be more than 1, but it cannot be too many. I will not find more than 9 points because every cell contains only 1 point. Am I done? Are there any more cells that I need to check? Remember, the grid size is D of S3 half. So theoretically, if P4 is close to the edge and P3 would have been just here, then it can also create a new closest pair. So I need to check also the 25 neighbors. Every cell that is 2 hops. But what about P3 that is outside this distance? If I have a point right here, I definitely don't need to check it because the distance from my finger to P4 is at least D of Si half plus D of Si half, maybe more because of diagonal. Definitely it will not be a point right here with my finger will not be a new closest pair. So how many cells do I need to check altogether? 25. Right? 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5. I need to check all these 25 cells. I will not find 25 points, but let's say that every cell contains a point. Maybe it cannot be, but even if it is, it's no more than 25 points constant. So I perform a constant number of queries in my hash table. And for each point that I do discover, like P4 over here, I check the distance from the newcomer P4 to each one of these new points in the closed neighborhood, check the distance, and ask, hey, d over si, did it goes down or did it stay the same? And if the distance stays the same, I'll be very happy, because then all I need to do in terms of data structure is insert P4 into my hash table and do absolutely nothing. That is, if by adding the points d over si plus 1 is the same as d over si, then it's just the insert into the hash table. Constant work. On the other hand, if d over si, that is the closest distance before adding P4, the closest distance is larger than the distance that I'll find now, I'll have to work much more. I'll have to rehash all the points that I've seen so far. And now, we'll see it in the next slide. To summarize what's happening here, to determine whether d over si is decreasing, strictly decreasing, or stays the same, do perform a query in the cell of P4 of Pi plus 1 plus the cells which are just around it, plus the cells which are just around it. It was 25 queries. In the homework, I'll ask you what happened in 3D. It will also be a constant, but different. And because every such cell contains at most one point, it's great. Constant work, just to check if d over si has changed. No, because each one is one query in the hash table, and query in the hash table, if you know what you're doing, should take constant time. The expected work is constant. Okay, so here is the algorithm. I have S2, that is P1 and P2, my first 2 points that I picked. I construct the hash table for them. And now for I equal 2, 3, 4, all the way to n minus 1, I check if Pi plus 1 defines a new closest pair, decrease the closest pair. I'm using the hash table that I created so far to check if the distance of the closest pair, because of adding Pi plus 1, once I'm adding Pi plus 1, did the distance decrease? If the distance decreased, if the distance did not decrease, then I knew what will happen in the future. My grid stays the same. And by the way, just to make sure, the grid is an abstract, imaginary thing. It's part of my imaginary world. But I don't really construct all these lines over there. But it's infinitely many cells, just the way that I like to think about the world as subdividing into cells. But the grid stays the same, the cell size, which is not imaginary, stays the same, the hash table stays the same. All you need to do, if d over si and d over si plus 1 are the same, did not decrease, then just insert Pi plus 1 into the hash table that you had, and you're done. Move to Pi plus 2. If the distance did decrease, then you're computing the new closest pair. Pi plus 1 must be one of the elements that participate in the new closest pair. And rehash everything, which takes linear times in I work, if you do have to rehash. What would be the running time? Not too hard. I'm referring to the distances here, but every time that I'm adding a point, the distance decreases a bit. Every time that I'm adding a point, the distance will decrease, and every time that I'm adding a point, I need to spend linear time to rehash everything. So it's omega of n squared. 1 plus 2 plus 3 plus all the way up to it, which is probably much slower because of all the ifs and the hash table and everything. It's much slower than just check all pairs of points immediately. But we already had an n square algorithm. The naive approach gave us the n square of checking all pairs. So why do I do all this gymnastic? Everybody agrees the worst case of this algorithm is is linear, is n square. That is, I gain absolutely nothing. So version 2 of the algorithm is very similar. All it says is that take all the points that you have, and just before you insert them, create a random permutation of the points. Create a random permutation of the points. Change their orders. Every permutation should have the same probability. How are we creating a random permutations of the numbers k1, k2, k3, and k4? N equals 4. I'll pick I, which is, let's say that R&D returns a number between 0 and 1. Random returns a value between 0 and 1. I take this value between 0 and 1, multiply by n, and take, if this is 1 all the way to n, then I'll take the ceiling. That would be a random index. It could be either the first one or the second one or the third one or the fourth one with equal probability. Okay, that's how I find the last element of my random permutation. The last element of my random permutation would be picked using this randomized approach. Right. But now I have a problem, as you were asked in homework 2, I think. One of the homework questions asked you, how do you create a random permutation? Where the problem was, how do I make sure that the next element that I pick will not be one of the elements that I picked already? So what I'm going to do is, let's say that I pick K2. I'll replace K2 with the last element, Kn. I picked I equals 2. I'll replace K2 with Kn, K4 in this case. So this random element is now here at the middle. Set n equals n minus 1. That is, from now on, my next element is only about the first 3 elements. And repeat. That is, the last element now is being stuck. You all hopefully figure it out by now because there is a deadline. Today, if you didn't, then that's a linear algorithm. That's the answer of this problem. So I create a random permutation. And after that, I just run the very same algorithm. I want to remind you the problem of computing the maximum. I want to remind you something very, very similar to the question that we discussed about how many times do I update the maximum when I pick elements at random. So in this case, I have an array A of only keys. That is, I just have in this array A, it's not this array, over there. Here I have only keys, only numbers, but it's random permutation. and I'm running from I goes from 1 to n, and asking how many times do I update the maximum element. And we asked what is a probability. Let's call this number, what is mi, the maximum, it's the ith step. And I wanted to ask what's the probability that we updated m at step I. Let's make sure that the camera likes this. I wanted to ask what is the probability that we updated the maximum at step number I? And the answer was that this probability is, help? This probability was 1 over I. And the reason was that we used essentially backward analysis. What is backward analysis? Let's assume that I already picked who will be the elements at A1, 2, and I. All the numbers, I already picked all the numbers from 1 to I, but now each permutation of them is equally likely. Each permutation of these numbers is equally likely. What does it mean that I updated the maximum at the ith step? It means that the maximum was the last element that I approached from here. So I have K1, K2, K3, let's say, and one of them is special, is unique, because it's a maximum or the minimum or some other property that makes it unique. All I need that it will be unique. I don't need any properties. It is that in any subset of my elements, there will be a unique such element. Now when I take a random permutation of the elements, and this unique element should not depend on the order, of course. You show me the elements, I'll tell you who is this special guy. Doesn't depend on the order. What's the probability that the special guy is at the last? It's the same probability that the special guy will be one before the last, the same probability that it will be the first. Right? So it's completely symmetric. It's called backward analysis. And it really made a revolution. This very simple idea really made a revolution in the algorithmic world. That people found much simpler way to understand and design algorithms. Why do we call it backward analysis? Because we think about it as, let's assume that we already picked all these numbers. The order doesn't matter. The maximum of these three elements doesn't matter at which order I pick. Once I decided that that's the first three, their order doesn't matter. And now I'll pick one at random. I like reverse time, going backward. That is, one of these elements will now be removed. What's my chances that I removed the maximum? Is the same chance that I removed each one of the other guys. One over I. But let's say that I put and now I removed it. Change my mind. Okay. Back to our closest pair question. So let's assume that the distances are all different. I don't have two pairs that defines exactly the same distance. If this assumption doesn't hold, it actually works for my benefit. It even makes the algorithm a bit faster. But I'll assume that the closest pair of every subset is unique. Closest pair of every subset is unique. So my array contains, say, this is Si at some order. Again, I'm doing this mental trick of assuming that I do the permutation of all the elements by two steps. I first decide who will be the first I elements, and then I'll decide at which order they'll appear. So here are the elements. There is a closest pair and it's unique. Two of these elements are red. Maybe it's 2 and 3, maybe it's 3 and 4, I don't know. Two of these elements are the special ones, the ones that define the closest pair of this subset. What's the probability is that at the I step, I'll pick when I'm moving from S3 to S4, what's the probability that the last element is red, given that there are two red elements? Well, it could be either this one or this one. 1 over I if it's this one, 1 over I if it's this one. So the probability that the I plus 1 points that I added participate in the closest pair of all the points so far is 2 over I. It's just a two-dimensional equivalent of the maximum or the minimum. But instead of the maximum determined by one element, the maximum determined by 2. But again, once you decide there are 2 points that define the closest pair, the distance or any other property is completely irrelevant. 2 are special. What's the chance that one of the special points will be the I plus 1 point? Since every permutation is equally likely, the probability that this guy will be the I plus 1 is 1 over I plus 1, the same with probability that this guy. What happens if the I plus 1 element is not one of the two red guys? Then d of Si stays d of Si plus 1. And I don't need to rehash. And I'm lazy and I really like it, that I don't need to do a lot of work. Everybody agrees? There is kind of small probability, only 2 over I plus 1, that I need to rehash. The same idea that we saw in the one-dimensional problem of finding the maximum or finding the minimum. The same will be for any other properties that I'll take. Give me a few nice ideas for homework. And the same idea that we are using in linear programming, and you'll see very soon, for this class. Same backward analysis. There are 2 special elements. Every permutation is equally likely. The work that I spend at the I step, the chance that I need to do all this work is only 2 over I plus 1. By the way, you notice that it's kind of cool how things are balanced each other. Right? If I do need to work here, if I do need to rehash, then the larger I is, the more work I need to do. But the probability that I have to do it will decrease, so they'll cancel each other. So let's do it formally. I want to define a random variable, a flag, that depending only on the order. And to make sure, the randomness is not randomness of the data. I don't assume that the points are taken from some distribution of points. You are with all the bad corners of your personality you design, the worst input for me that can really cause my algorithm to fail. And the only thing that I can remedy the bad input that you gave me was to take different permutations. But it's completely up to my control. I don't have control about the input. I just have control about the order at which I enter the points into my input. What's cool about this algorithm is that it works even if the points appears as a string. Like you're listening to some space telescope, you don't want to store all the points in a huge area. You have a stream of points, and you want to keep several properties. A lot of this trick can still work, but it's much less obvious. At the moment, I assume that all my data is available in some area, and I just can scramble the order. So once the order is fixed, then there is a flag, xi. This flag is on if, when I'm adding pi plus 1, the distance really decreased. D of si plus 1 is strictly smaller than d of si. It can never be larger, but it can be equal. So the flag is on, xi is 1, if d of si is strictly smaller, and if the d of si, the distance of the closest pair, stays the same, xi is 0. The order is fixed. How much work is done by the algorithm? Assuming that hashing takes order I time and deleting the hashing takes a constant. What will be the work that I spend? It's the first step. I start from I equals 3, so it's the first step I'm spending a constant plus 3, but only if I need to do the rehashing. It's 3 elements to reinsert 3 points, but only if I need to do the rehashing, only if d of S3 is smaller than d of S2. Now I'm adding P4. How much work? 1 plus, if x4 is 1, then linear in 4. It was the order I that we saw for the rehashing. For the I step, it would be 1, constant no matter what, you have to spend this constant, plus I times, only if xi is 1. Otherwise, you don't need to rehash, and you are at the I step getting away with just this 1 over here. So we look at all this sum, which is what? All these ones sums up to n. Yeah, it's linear algorithm. You cannot read an input of linear size in less than n time, plus sigma of I times xi. Xi is 0 or 1. Yes or no? You had to rehash or not? We didn't have to rehash. What we want to do is what we want to know is what the expected work. What is the expected work of this algorithm if I do this random scrambling? Now xi becomes a random variable. It's depending on the order that I inserted the points. So what is E of this monster? It is E of, remind everybody, we saw it multiple times, but let's write it once again. E of two random variables, x plus y, is E of x plus E of y. For any two random variables, a bit counterintuitive because it doesn't care if it's depending on each other, if one affects the other in any way. This is still the expected work, and if x and y are also Boolean variables 0 or 1, then it's just probability of x plus probability that x equal 1 plus probability that y equals 1. The same formula. And what we didn't use so far, but we are going to, is to use the expected value of alpha times x. Alpha is a constant. Is just alpha times the expected value of x. Okay, so I want to know what the expected work of the algorithm, which is n plus the E goes into the sigma. Expected of sum is the sum of the expectation. The I have I times xi. I goes out for the expected. I is the alpha that you see on the whiteboard. So it's plus sigma of I times E of xi, which is n plus I times, what is E of xi? Xi is Boolean. We just said flag, yes or no. Expected value of variable is sum of all its values times the probability that it happens, which in this case is just the probability that it's 1. So I times probability that xi equal 1. We're all done. which is n plus sigma of I times what's the probability that xi equal 1 is 2 over I. The two i's cancel each other, and we are saying that the expected walk at the I step is only 3. If you run the algorithm a million times, but for the same points, but each time pick a different permutation, you ask what is the average walk on all these million experiments that I did at step I, no matter what is I, it will be a constant, 3. And the overall running time is linear. Everybody understand? Everybody follow, then anybody understand what's the real big idea behind it? The backward analysis was one big idea, and the other one that it happens to be linear because as I increases, that is, if something bad happens, hashing takes more time, but the probability that something bad happens goes in inverse linear. So they cancel each other. Okay, and we are done with the closest pair. I'll ask you a few questions in the homework about it, obviously. And let's go into linear programming. Okay. So, let's talk about let's talk about designing diets. People that takes that we are going to go. People that took it already. Some of you have seen me talking about it last week. So we have the diet problem. I'm going to help you design a really efficient yet healthy, economical yet very healthy diet. There is a little caveat here. You have to switch to eating bananas and oranges only. Nothing else but bananas and oranges. And we are going to optimize how many bananas and how many oranges you're going to have. I'll indicate the bananas by X, and I'll indicate the oranges by Y. So I have two variables. We like geometry. It will be a point somewhere in the XY plane. And I will try to optimize some cost function but I'll make sure that you're getting enough vitamin A, B, C, and D, nevertheless. Very quick reminder about what is a half plane. If you look at all the points in the plane x and y such that y is larger than x, what is the line y equal x? This is just this line. Where the points for which y is larger than x, they are in a half plane. Half planes are all the points on one side of a line. Okay, so all the xy such that y is larger than x are all the points over here. All the points y for which y is larger than x minus x plus 3. Well, where is the line y equal minus x plus 3? It's going down. It's moving a bit. If you put x equals 0, it equals 3. And it's going down, and all the points to be on the line means that y of my figure equal to exactly x minus 3. If I added y a bit more, then I'm inside the half plane. To be precise, the half planes I'm already when I'm on the line. The half planes containing its boundaries. So the two half planes share all the points on their boundaries. And now if I have two half planes, I can speak about the intersections. All the points that are in the first and in the second. The first half planes were all the points on this side. The second half planes, H2 by the way, H2, all the points on this side, and every point in this bluish region is both inside H1 and inside H2. Okay. Another half planes, all the xy such that y is smaller than 3. So where is x in this equation? X doesn't appear in the quadrant. X doesn't appear. It's all the points xy such that no matter what is x, y is at most 3. Where is the line y equals 3? It's horizontal line. And the half planes are all the points on this line or below. And now I can ask what is the intersection of these three half planes, this region. Okay. Just a definition. When can I say that a point is that a shape is convex? A shape is convex if pick any pair of points inside the shape, pick any pair of points P and Q inside the shape, look at the line segment, this piece of the straight line that connects them between P and Q. Pick any point along this segment. To be convex, no matter what are the points P and Q inside the shape, and no matter which point I picked on the convex, this point must be inside the shape. So this shape, well, this segment is completely inside S, so this segment check mark, it's fine. But if I'll pick this segment between these 2 points, I'm outside the shape. Not good. So this is not convex. By the way, it doesn't make it concave. The opposite of convex is not convex. It's not a common mistake. It doesn't make it concave. So that would be will be non-convex. Disk will be convex. Square will be convex. What about the whole plane? All the points xy? Absolutely. It contains all the points, in particular all the points of the segment. Half planes, convex. Half plane is also convex. Little lemma, very easy to prove, that if I have two shapes, any two shapes that are convex, I tell you that they are convex, I guarantee, and you look at their intersection, all the points in their intersection. Pick any 2 points, P and Q, in the convex. One belongs to A, one A. They are both P and Q are in the intersection, so they both belong to A, they both belong to B. The segment between them, because A and B are convex, is also both inside A and B, so this segment is also in the intersection. Quite obvious. Meaning that my half planes are convex and their intersection is convex as well. We can skip at the moment the little review of linear algebra, and let's talk about the diet problem. So I want to find X number of bananas per day, Y number of oranges, under which constraints. I'll have a lot of constants. X and Y is what I need to find, and somebody gave me a lot of constants, a lot of data. What are these constants? AI, comma 1 is how many units of vitamin I, A, B, C, D, I equal 1, 2, 3, 4. How many units of vitamin 1 there is in a single banana? That's what the constant AI1 tells me. AI2 tells me how many units of vitamin I there is in an orange. Data that I got from elsewhere. If you like vectors, AI makes it a vector. If you don't, that's fine, you don't need it. What other things do I know from my health sources? That I need, from vitamin I need at least BI units per day, otherwise my diet is not healthy. What does it mean? What is AI, if you like vectors? The vector X is just it's confusing. I'm using X for two meanings, but that X with vector sign and boldface, and that's X with italic and without arrow. So the vector X consists of X1, X2, or X and Y, to keep it simple. And let's think about A dot product X. How many of you have seen dot products before? How many of you have not? No, not necessarily, just it's a shortcut. When I multiply two vectors, dot product, I take the first component of AI, multiply by the first component of X, take the second component of the vector AI, multiply by the second component of Y, and sum them up. We actually will use it quite a lot in hashing, by the way. So, what is AI times the vector X? Takes AI1 times X. What does it mean? How many units of vitamin I do I get from bananas, given that I eat, say, X, 3 bananas per day, and each one there are 7 units. So from vitamin I got these many units just from the bananas, plus similar set of units that I got from the same vitamin, but from the amount of oranges. I eat 1 orange per day, times in each of them there is 20 units of vitamin I. I sum up, because it's the same vitamins, it must be at least BI. I need to pick XI, YI such that this condition is satisfied for every vitamin. That is, AI dot product X must be larger than the constant BI, the minimum health requirement. Okay, and I'll have it in the app for 4 vitamins, in general, as many vitamins as you want. By the way, if you don't like that your diet consists only of oranges and bananas, you want avocados as well, you can still use linear programming, but then it will be linear programming in 3D, not in 2D, obviously. So there will be 3 unknowns. What else am I given? I will be given a cost vector C. Vector C consists of several parameters. What are they? C1 is how much a banana costs in dollars. C2 is how much an orange costs in dollars. How much do I need to spend per day? C1 times how many bananas I'm going to get, plus how many oranges I'm going to get, times the price of each one respectively. That's how much I'm going to spend. Okay, you got what So here are my constraints. For vitamin 1, in banana, you have, from vitamin 1, vitamin A. Banana contains 7 units. Orange contains 1 unit. Somebody told me. And you must have at least 65 units to make the diet healthy, which I can make it into a linear inequality, which will define a hyperplasicity base, which is what? It would be 7 times the number of bananas you're eating per day, plus 1 times y, how many bananas you're going to get. This gives you the overall units of vitamin A. It must be at least 65. Let's see how it looks geometrically. So every point in the plane here, every point over here will be just a diet. The point xy, wherever xy is, x equal 80, y equal also about 80, it will cost me, that means that I'm planning to eat 80 units, any 80 oranges, 80 bananas per day. Every point is a planned diet. Which diets do I look at that just barely meet vitamin I? I'm going to solve this inequality just with equality. So 7x plus y equals 65. And you're generating this line over here. So there are some diets that make sense, and there is some diets here that includes minus eating oranges. I don't want to think about it. We can ignore everything that is negative, but every point over here is a diet that barely gives me the minimum of vitamin A. Again, every point on this line, you're just getting 65 units of vitamin A, which is a bare minimum. Where do you have diets that are healthy in terms of vitamin A? Every point to the right side of this line, you're getting enough many vitamin A that you need. Everything to the right side of this line, you're getting enough many vitamins A as you need. And oh, by the way, I decided that eating more than oranges per day, 80 oranges per day is too much, so I cut it just for visualization. But that's essentially all the points that vitamin A is satisfied. I still didn't speak about price. Let's take vitamin A off. Let's look at vitamin B. Vitamin B, what's the equation? 4x plus 2y. 4x plus 2y. How many units of vitamin B are you getting per day? Equals 70. If x and y satisfy it, you are just getting the bare minimum amount of vitamin B. You are on this line. So where diets that you're getting enough many vitamin B is if you're increasing Y, taking more oranges, of course it's even more healthy, or at least allowable. So here are all the units of vitamin B that I need. All good? Everybody agrees? There are diets that I get enough vitamin A and vitamin B. Let's look at it. I put vitamin A once again, but I'll ask you to play with this applet at home to answer a few simple questions. Look at the intersection of these two half planes. Like every point in the intersection of these two half planes, you're getting enough vitamin A and vitamin B. Every point here, you're getting enough vitamin B, but not enough vitamin A, and vice versa. 4 points here. So we are only going to consider points in the intersection of all of them. I have another 2 vitamins to consider. Here are vitamins C and D from these 2 equations over here. And the diets that they are defining is the intersection of these 2 half planes. But these 2 half planes define this region. Then you're getting enough vitamin C and D. Let's put it all together. All the healthy diets. Here I take the intersection of these 4 half planes, and you see that it creates a convex polygon. In this case, it's polygon. It's convex because it's intersection of convex shapes, and it will really, really help us in finding the optimal solution. So far, I didn't say anything about the cost. Let's turn off the diet for a second, and let's start to increase our budget cost. So now I'm saying that my budget is $37, and by the way, the cost of a banana is 1.6, cost of an orange is 3. Where do I have, well, diets that I can afford? Ignore health. Where are diets that I can afford? With a budget of $37, the most expensive diet that I can still afford are exactly on this line. Which line? This times X plus this times Y equals my budget. Now, a very important point would be, I cannot really afford any diets, any healthy diets with in this budget, but if I put all the healthy diets back again, look what happened when I slowly increase my budget. A very, very important property here is that as I'm changing my budget, I'm not changing my cost of orange and cost of banana, but I'm increasing my budget. What happened to the orientation of this line? The more budget that I have, the line changes. What is this point? That's how much, what I can get, which diet I can get if I spend all the money for bananas. Here is if I spend all the money for oranges. And being on the line is if I'm spending any combination. But now when I'm changing my daily budget, slowly increasing it, what happens to this line? It moves parallel to itself. Remember, it moves parallel to itself. And it has a nice property. If I look at this vector, that's a cost vector. That's a vector of how much a banana and how much an orange cost, this direction. It doesn't depend on my budget, it actually depends on the ratio of the cost. This vector is always perpendicular to this line. So now it gives me the first observation that will help me in the algorithm. What am I looking for? I'm looking for a diet that are healthy and will cost as much as possible. Either healthy diets right now with a budget of $157 per day, yes. Everything in the shaded area is both healthy and I can afford. What am I looking for? I'm looking for the cheapest diet that I can still afford. So I'll take this line and slowly, it's not the algorithm, but it's a claim that I'm trying to make. I'll swing this line slowly down, 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 spending less and less money per day until at the very last moment, I just have a single point that is still left, and that would be my optimal diet. So instead, what did I do with this little trick? It's not the algorithm that I'm going to describe of moving it, but what I hopefully was able to convince you is that I don't face the problem of look for a good diet in the whole infinite many combination of X and Y. All you need to do as a first step is look at the intersection of the healthy diets, and if there and look only at vertices of this intersection. Because if you have a point in the intersection that you can afford, then you also have a vertex that you can afford. I mean, possibly I can change this line, give me a second, possibly for different combination of bananas and bananas cost and orange cost, possibly you have a spectrum of a lot of optimal points. Everything along this edge are all diets with the same price. As I'm walking along this edge, all the diets are with the same price, and all of them I can afford and all of them are healthy. But I'm not going to search for points along this edge. I'm very happy that I have this observation that it's enough to check optimality among vertices of this convex region. So my first step toward an algorithm in 2D and in higher dimensions would be it's enough to check vertices of what we call the feasible region. Think about this feasible region. Don't necessarily build all of it. It will be hard in higher dimensions. But you can build all of it directly in 2D, check all the vertices of the intersection. One of them will be the one with the optimal cost, and you're only checking feasible ones. Okay, and from here we will both move towards the incremental algorithm that added half plants one by one, and surprise, surprise, we will see that just similar to the points, something that we need to change as we are adding one more vitamin, the expected work will be a constant using the very similar arguments. Why they are similar? Because the vertex, the optimal vertex is determined by two special half planes, and the chances that when you're inserting a half plane, one of them is one of the two that determine the special optimum will be 2 over I plus 1, just as in the points. So the expected work of inserting one half plane will be a constant. But there is quite a few details that I need to fill you up about it. Other one will be the simplex algorithm that we'll discuss that works in higher dimensions, as well as the integer linear programming that we'll discuss, that we'll see the applications of it. Thanks, Manny. Bye.